I don't know how to give a general argument, but let us simplify and try to use the equations of this martingale Markov chain. So, let us assume that E0 and En are the only two closed sets because they are absorbing states. All the others, E1 to En minus 1, they are transient. Okay, so their probabilities in the end, probability of reaching to transient is 0. So, what happens if you assume that? So, let us assume it is an assumption that E1 to En minus 1 are transient. Okay, which will immediately tell you that Pjk tends to 0 for k 1 to n minus 1. So, if this happens, if Pjk tends to 0 for all these states, then using this martingale property, sigma Pjk times k equal to j, what you can deduce is sigma Pjk times k equal to j implies that, and notice that k here is positive, right, k equal to 0 does not contribute, so it is really k positive. So, this implies that and also after a long time, right. So, this means that when you look at P Jn times n, this tends to the whole thing as n tends at small n tends to infinity. Right. So, in the limit, the only term that is contributing here is Pjn. So, Pjn minus 1 dot dot Pj1 and also Pj0, they are not contributing anything in this expectation. So, you get this, from which you deduce that Pjn is tending to j by n for all j 1 to n minus 1. So, if you are in a transient state, if you start from a transient state j, then the chance of reaching En, E big N after a long time is exactly j by big N. And also P, if you started from 0, then it is 1 minus j by n. Right. So, we have these two probabilities are positive, the other probabilities, sorry, it is not like this, j0, going from j to 0 versus going j to big N. We deduce that, and what this means is that if j is greater than n by 2, then you are reaching En. The process tends to En higher, right, because this j by n is greater than half. So, it is actually with more than half probability you will be reaching En. On the other hand, if j is less than n by 2, then with probability more than half, it will be tending to E0. So, if A types are more, then A types will dominate and they will become, all the particles will become A type. If A types are less, then in the end all the particles will become B type, right. So, what you learn is that the dominating gene ultimately wins. Either everything becomes A type or everything becomes B type. That is what we have learned. So, if this is assuming that this simplification that other states are transient. Okay, so, you do not get stuck in them. In the end, you are either in E0 or En. So, that finishes this outstanding example of Markov chain in cell genetics, and you can study many such examples. This is a simplified model of evolution. Okay, so let us see some other practical examples which are not really based on Markov chains. So, let us now take a detour to some practical questions. Of probability. Right. So, in practice, how do you create a probabilistic process? So, the first example is from uniform sampling. From 0 to m minus 1. So, when you say that in an algorithm you want to pick a random element less than m, which is a non-negative integer, how do you do that? Right, in an algorithm, how do you actually pick a random element? So, you can always assume that there is a coin to be flipped, that is there, but using coin flipping, how do you achieve this? That is a practical question. So, given an integer m and unbiased coin, design an algorithm to pick a random number x in this range. How do you do this? By using unbiased coin flips. So, the idea here is that you toss the coin log of m to base 2, okay, many times. That is the idea, but the problem is that this will give you k bits, but this is more information, this might be more information than you were asked. So, this, if you look at these k bits and look at the number which this binary string represents, that may be a number more than m, right. So, you are not in this range. So, how do you get in this range? By so many coin flips. So, the problem is that this might be extra, this, so x might be more than m minus 1. So, the binary string might give this x greater than m minus 1. Right. So, what will you do then? How do you come back How do you come back to this range? So let's see that algorithm. So first you compute k to be log of m to base 2. Then you toss the coin k times. To get x, which is the number out of this binary string. So head is 1, tail is 0, and that gives you 1 and 0, and that gives you k bit string, right? So that's the bits are xi's. Xi is 0 or 1 in the ith toss, right? So you have gotten this number x, but as I said, this number may be more than m, so it doesn't help. So what you do is that in that case, if x is exceeding m minus 1, then you throw it away, repeat the experiment. So go to 1. Else you output this x. So if it is in the range, output it. If it's outside the range, then throw it away, repeat the experiment. So that's a simple algorithm. Why does it work? So let us see for t in the range 0 to m minus 1. Let's see what is the probability of output is t. So what is the probability that the algorithm outputs t? So this probability is that x comes out to be t, right, which is subject to x in the range 0 to m minus 1. So given that you are in else, what is the chance? Given that the algorithm is outputting, what is the chance that it is t? Right, that exactly is the probability you are interested in. Because if x is not in 0 to m minus 1, then there won't be an output, right? And that comes out to be, so this is equal to probability x is t and x is in 0 to m minus 1 divided by the probability that x is in 0 to m minus 1. So the first event is just that probability is x equal to t, which is what is the chance that this number is picked, right? That is, there are 2 raised to k possibilities, out of which only one is favorable. So it's 1 over 2 raised to k, and x falling in this 0 to m minus 1 range, that is m possibilities out of 2 raised to k. So you get 1 by m. Right, so this is uniform probability. Okay, so this process will give you a t, any t in the range with equal probability. There is no difference. That's the point. By changing t, you are not increasing the probability or decreasing it. And it's also true that for all t not in this range, the probability of output being t is 0, right. So, if t is in the range, probability is 1 by n. If t is not in the range, then the probability of outputting is 0, because then this step 2 will be followed, and it will repeat step 1 and not output. But this doesn't seem to be a good practical algorithm, because there is a go to, it is an infinite loop, right. So, but the go to may execute infinitely many times. That is very bad, it is an infinite loop. Maybe every time you do the experiment in step 1, it is outside the range, and then you are in an infinite loop. The algorithm is in an infinite loop, the answer never comes. So, yeah, that can happen, but let us try to see then expected number of steps, expected number of go to. So, let us do that. So, expected number of times 1 is executed. Okay, let us call it mu. So, you toss the first time, and next time it will be, you have to do it again if the value was more than m minus 1. So, in case it is in the range, which is the chance is m by 2 raised to k, right. Out of 2 raised to k numbers, 2 raised to k possibilities, x came out to be in the range, which is only m possibilities. So, then it is executed only once, or the first time it did not happen, it was outside the range, second time it was in the range. So, then it is 2 times, or the first 2 are bad, third time is good. It is an infinite sum, right. So, this will need some work. So, 1 time, 2 time, 3 time, and then the respective probability. So, let us do this work. What do you get? So, let me define delta here. Let delta be 1 minus m over 2 to the k. Now, the way we have defined k, m over 2 to the k will always be at least half. So, this is at most half. Okay, so, let me write this down. So, I can write it as 2 raised to k by m mu is equal to 1 plus delta times 2 plus delta square times 3 and so on, and I can multiply by delta this whole equation. So, I get 2 raised to k mu delta by m is equal to delta plus delta square 2 and so on, and then I take the difference of these two. So, if I take the difference, what do I get? 2 raised to k mu by m times 1 minus delta is 1 plus delta square. Delta is a fraction, so you do the geometric sum. So, this gives you what? So, 1 minus delta is m over 2 raised to k. So, you get On the left hand side you are left with mu, and on the right hand side you have 2 raised to k by m, and 2 raised to k by m is at most 2, right. So, that is what you get, that is the expectation. So, the go to or step 1 in the algorithm, that is expected to run only 2 times. So, let us note that down. The algorithm is expected to stop in only 2 times, right. So, 2k coin tosses. Okay, so it is not the case that you expect this to run infinitely many times in an infinite loop. It will actually this step 1 will happen only twice, and in that it will output x. Okay, so this is only log m many tosses that you are doing. So, in log m many steps you are able to sample in the range 0 to m minus 1, right. So, this is the most basic algorithm that you will need in probabilistic algorithms. Okay, let us now extend this a bit. What if you need k distinct numbers? What will you do then? Not just one number. So, sampling k numbers from the same range. You have seen a solution for k equal to 1, right, but now you want say 2 numbers which are different, and you want these numbers to come out in a uniformly distributed way. So, given k and m, you want to pick a random subset S of 0 to m minus 1 of size k. What is the idea now? So, the idea is you do something like you did in step 1. So, if the answer is not good, if the choice is not good, you repeat. Okay, so when you are picking the second element, if it is the same as first element, you repeat, and third element, if it is the same as first or second, you repeat. So, keep picking an element till you get a new one. Okay. So, let us see this algorithm, it is very similar. So, you start with the empty set and we will grow it slowly. So, for the ith element, what you will do is uniformly picked, so uniformly picked element in the range. So, use the previous algorithm. So, that will quickly give you a random element in the range, but that is only one. So, you add this in S, well, not so fast. First you have to check, in general you have to check whether it's a new element or not. So, if this element is already in S, then you go to two. If this is already in S, then it is not of any help, right? You have to repeat the uniform picking. Otherwise, it is a good element, it is a new element, so you will add. Right, and then you finish the for loop. You have, in the end, you have k distinct elements in S, and you output this S. Right, that is the simple algorithm to now sample k distinct numbers. So, what is the probability and how many steps are required? Let us check that quickly. So, let us analyze the iterations I equal to 1, I equal to 2, the first two iterations. So, consider two elements T1, T2 in the range. Now, let us look at the probability that set formed in the first two iterations has T1, T2, it is equal to T1, T2. What is that probability? So, this probability is equal to, in the first iteration T1 was found and then T2 was found, plus the symmetric one. Right. So, probability that in the first iteration T1 was found, since you uniformly picked in the range 0 to m minus 1, that is 1 by m. And then after picking this T1, the x will come out to be T2, correct x. It will come out to be T2 only when the choice is made from the m minus 1 things. So, this is 1 over m minus 1. Otherwise, this x will not be correct x, right, plus the same thing here. Okay, so, this becomes 2 over m minus 1, which is 1 over m choose 2, right. So, that is a uniform probability. Right. So, for distinct T1, T2, this set coming out to be obtained in 2 iterations, it is actually exactly what you wanted. So, we will finish this next time.